the next lecture by Danylo Babich from Paul Scherrer Institute, and he will talk about micro-XRD imaging of Mott insulators. Please go ahead.
So good afternoon. I hope that you can hear me. So I am Danylo Babich, and I am currently will present during my talk my research during my PhD, which I did in France in Institute of Material of Nantes. And currently I am working actually in Swiss Fair, and soon in almost 2 weeks I will start to construct the beamline on line to Ukraine project. But let me start from my current work, which is at Swissfeld, and basically all of you probably have heard wonderful talk of Mykola Bernal, where they performed nice X-ray absorption time result spectroscopy and X-ray emission spectroscopy. So at Bernina, we recently succeed to have it at much higher time resolution, which is around 15 femtosecond RMS, and I just took opportunity to advertise that we are also open for users, and we have wide possibility of optical pump, including X-ray, circular polarized X-ray, and also ultra-fast nonlinear optical parametric amplifier laser source, which is down to 10 femtosecond. But let me go back to something much more easier and something kind of, I will come back to time result measurements at the end of my talk. But let's start from something which humanity experienced since 100,000 years ago. And it was materials. And basically, for the moment, we have what kind of materials was important like 1,000 years ago. And if you ask a guy from Middle Age, he says that silex is better than silicon. And if you ask the guy from Industrial Revolution, he would say that iron would be better. But currently, if you ask yourself, definitely silicon or germanium or any other semiconductors are the very important materials uh, uh, as a very important materials for our computing parameters. However, if we take our devices or USB key, it contains on complementary metal oxide semiconductor transistor, and it takes a lot of space and a lot of efforts to produce it. And basically, for all of you heard about Moore's law, which is kind of predicting physical limitation of producing materials, and it would not work anymore soon. And for the moment, for the memory cells, we have 13 nanometers units, and fabrication of smaller, much smaller units would require a lot of investment. So in order to overpass such a dilemma, we should look for new materials and new physics which can be used. And one of candidates which I would like to introduce you would be the Mott insulator. And let me introduce you what exactly is Mott insulator. Mott insulator, it is actually, according to the classical bound theory, is a metal. It's a crystal with one unpaired electron per side. And in this case, you would expect the simple half-field bond structure, which is suggesting metallic behavior. However, in reality, the situation is completely different, because in such a system, you have very strong, higher than bandwidth on-site Colombian repulsion, which will split your system into two subbands and will open the insulated gap. And basically, playing with these two parameters, which is on-site Colombian repulsion and bandwidth, you can induce insulator to metal transition. And if you look on the simplified phase diagram, you can draw a line which will split insulator state to the correlated metal state. And the easiest way to tune it is by applying the pressure. When you apply pressure, basically you will increase the bandwidth, and you will create a kind of fuzzy particle peak exactly as Fermi energy, and you will close the gap. And basically this transition also related to volume change. Other option how you can do it is to, at equilibrium, is to change stoichiometry of your system. Basically dope your system with electronical field. And in such a case, you will change your Fermi level, and also would expect kind of living insulating state. The problem which we can see here, that both cases is not suitable for real electronic application because you cannot put the pressure cell or chemical laboratory into your computer. So I would suggest a second different way, which was suggested by my group, is to apply electric field. And here you can see a gallium tantalum selenium 8 Mott insulator, and you see the simple crystal connected by two electrodes, and via this electrodes you can apply electric pulse. And quite rapidly, as a certain non-volatile resistive switching regime, you are able to switch your resistivity of your sample from high to low resistivity state. And if you apply another slightly longer electric pulse back, the system can cycle from high to low resistivity state, and it really can be a prototype of flash memory. Here you can, on the slide, you can see that we succeed to do 20 nanosecond switching. Now our group is developing and we perform it much better and much smaller, can provide much smaller devices. However, the main problem that we were asking ourselves, what would be the mechanism of such a process? And through several steps of investigation, we realized that when you apply electric field, you have initial spark, which actually accelerate the hot carriers in your system and will launch avalanche multiplication of carriers, which would lead to metallicity creation in the system. And propagation of this filament would create propagation of this avalanche would create a metallic conductive filamentary path in your system. And basically, after electric pulse, depending how strong your electric field, it would be volatile or non-volatile regime. But this theory was suggested, but open question, which we were asking we are asking ourselves, what is the nature of the filamentary metallic phase? And what would be the links to the Mott physics of this phenomenon? So first, let's look on one of materials which I presented to you before. It's AM4Q8 system where you can have different elements for A, M, and Q. And it's also kind of classical Mott insulator, roughly at room temperature. And basically what we try to do, we succeed to apply electric field. We transited such a material, and basically we created conductive filament. And I just would like to notice that at the pressure, at low temperature, you have superconductivity phase in such a material. And basically, if you make resistivity versus temperature of transport measurements of this material, you can see that basically you have superconductivity state at low temperature, which basically can be canceled by magnetic field, which would mean that probably we are tuned by applying electric field, we tune such a system into the correlated metal state. And if you look further down this phase diagram, at low temperature, it will be superconductive. However, it just gave to us initial hints what can be the nature. And to move forward, we choose a different material, which is chromium doped vanadium oxide, which is an emblematic Mott insulator. And basically, first let me introduce such a system. So if you take vanadium oxide at room temperature without any chromium substitution, you will be a paramagnetic at the paramagnetic metallic phase. But if you replace part of the vanadium atoms by the chromium, you will basically tune your system into paramagnetic Mott insulator state. And the idea would be, let's try to apply pressure on such a system and see what would happen. Because we should expect a drop of volume in such a system in the case if we will have transition. So unfortunately, so basically an electric field. So we prepared the special device with electrodes and these materials in film on top of it, and we tried to induce phase transition or resistivity switching in such device. And if you make IFM and conductive IFM map on such a material on pristine state, then let's make a Raman characterization of such material. And then let's apply electric field. Let's switch such a system to low resistivity state. And let's check. Now we have some kind of conductivity path created in such a system. And then Raman fingerprint on such a system shows that we have switching of Raman mode. And basically, we thought that we know that we are doing some kind of, can be doing some kind of pressure, similar to the pressure effect switching. And what we tried to think that let's take such a material and let's put it in diamond anvil cell and let's check what would be the Raman fingerprint for correlated metal and for insulating phase. So basically, we can see that completely similar shift we can observe by applying pressure and switching our material to correlated metal in the diamond anvil cell. So we have two ingredients which is suggestion towards it. By applying electric field, we probably change the lattice parameters and induce the state similar which can appear under pressure application. So, which is, you can directly see here. Here it's pressure applied shift of Raman mode, and here it is basically electrically field applied change. So what is this phase? And now the story turns to instrument which probably will build under Light to Ukraine project, but it already exists since a year. So it's a Micro-XRD beamline at Swiss light source. And what we tried to do, we tried to study this device and this transited sample by Micro-XRD diffraction. And what we realized that exactly at the place where conductive path was showing and Raman was showing some changes, we see a shift of diffraction peaks. And if you calculate all A and B lattice parameters, you will definitely observe the change of volume, which would indicate a direct confirmation of local compression of your filament in the system. So we basically, thanks to this amazing study, we clarified the nature of phase which was induced by electric, which was created after electric mode transition. And basically, in order to summarize, we learn a lot. So first of all, we see that Raman can show a shift of Raman. We can see Raman shift of Raman modes, and especially softening when you apply pressure, which is kind of a trivial result, which also would be published soon. Then we see that electric mode transition induce a local filamentary path and local compression of lattice of the material. And it's opened new perspectives into the different other applications. For example, we also can make it probably faster by applying terahertz, laser pulse, or doing another studies. And just to finish, I would like to show you last paper which was published 1 month ago by my former group, and I was also performing these studies. Is basically we tried to do exactly the same, but by photoexcitation, and we definitely succeed to change lattice to induce a volume drop by applying the ultra-fast laser pulse into your into the Mott insulator. And luckily, kind of the message, home take message of this research is basically when you start from steady state measurements, then you progress with your studies, and you turn out that it's open your door for another research which is related to the ultra-fast measurements and time result measurements. For example, this last paper was published thanks to our measurement at time result beamline and femtomax in loop, and basically we have in kind of summarizing both side of synchrotron community, which is synchrotron and free electron lasers. Thank you for your attention. I'm looking forward for your questions.
Thank you very much for your very wonderful presentation and for keeping your time. So we have time for a few questions. Please welcome. So I see that Marcin Shikora has a question. Please.
Thank you, Danylo, for a very nice talk. I'm wondering about this comparison of this electrically induced transition and the pressure transition. Is it exactly the same material? I mean, of course, in a diamond anvil cell, probably it's not a thin film, but yeah,
Of
I
course,
was
in diamond
wondering.
anvil cell we have used in diamond anvil cell we have used a single crystal. That's true. But the chromium percentage was exactly the same. We checked it by EDX and also by X-ray diffraction. You can check stoichiometry. Of course, the difference between the crystals that you can have kind of lattice and you have long order, and it was not epitaxial thin film, it was polycrystalline thin film.
Yeah,
So basically, you have grains, and probably if you have grains, you can more easily transit single grain instead of transiting entire crystal. But we can see this transition in crystals, and now in 1 month we got the beam time at diamond where we will look on the diffraction in crystals. We can try in situ transit the crystal and check by diffuse scattering the effect.
you already partly answered to my other question, if I may ask.
Yes.
If the film, of course, is polycrystalline, so probably there is not much effect of strain related to the substrate. But I was wondering if you also see some effects because you probably prepare your sample lithographically. Would you see that the lithography parameters, I don't know, the etching and so on, would that influence the effect? Have you observed any of this kind?
Unfortunately, I think I didn't observe, but lithography procedure is in some way require re-annealing of samples. So usually, if you just take simple without lithography preparation and simple with lithography preparation, there is no huge difference. That's I would say. But basically, there is definitely difference with crystals. It's much tougher to transit because you have kind of clamping induced by lattice, and when you have polycrystalline grains, they are
Yeah,
easy.
roughly. Yeah.
Yeah.
Okay, thank you very much.
We have time for one more short question, maybe.
A question, just this phase diagram. It's probably iconic phase diagram for this material, but I'm wondering based on which quantity, measured quantity it is made. What it is resistivity or what?
Which phase diagram? Because I have, for example,
I mean,
basically phase diagram related
phase diagram which you used last.
at the beginning or at the end. Let me share my screen just a second.
I mean, when you have Mott transition, it is transition in what? What is measured?
So this is pressure. Oh,
I
and
mean,
basically, if I will show that schematic, but here is a real phase diagram of chromium doped vanadium oxide. So you can have pressure in this, and here you have chromium doping.
here you have, let's say, blue, this is Mott insulator and correlated metal region. And
Yes.
this in between. What is changed? What people are measuring to draw this line?
Yeah, so basically, usually people first of all measuring transport, performing transport measurements.
I'm curious how.
And also we were measuring actually exactly the transition we see volume change, drop.
What has changed?
Volume drop, but also you have orbital configuration on top. As exactly at the transition, you have change of volume, of cell volume.
Okay, but it's just interesting to have a look on resistivity, not resistivity. Yeah, resistivity is temperature, how it behaves.
Yeah, that's actually we have basically, usually I don't show it here, but first when you transit, you check the resistivity versus temperature. And you see basically, oh, I don't know if I have it here. But basically, for example, for vanadium oxide, we also try to perform studies on crystal. And what we have seen that, so sorry, I just downgraded my presentation because I just deleted the slides in order to keep time. So imagine now this is vanadium oxide. You have basically, you're in Mott insulator state, and you have actually transitioned from non-insulator to anti-paramagnetic Mott insulator. And basically, it's quite characteristic. But once you transit your system and you make resistivity resonance measurement, this is before transition, then it's after transition. And basically, you see that now this phase under temperature-induced phase transition from Mott insulated phase to antiparamagnetic phase is somewhere here, which would be somehow indicate this position in the phase diagram. And next part, if you make a cycle, which we are thinking, so you heat and cool down again, this position is switched because due to the cycling, you probably relax your filament slightly, and basically strain-induced stuff is different. Now you're slightly moving towards this direction. And then basically that's, if it was your question and if you answered.
I wanted to see this curve. Thank you.
Okay, thank you again for the talk. And